All right, let's jump right into this. Picture this scenario. You're cruising at 35,000 feet in a commercial airliner, just relaxing in your seat, when suddenly, the engines go dead quiet. You haven't suffered some catastrophic mechanical failure. You have literally just run completely out of fuel mid-flight. I know, it sounds exactly like a Hollywood thriller, but this actually happened in real life. The aircraft we're talking about was a terrifying 15,000 liters short of the 22,300 kilograms of fuel it desperately needed to safely finish its journey. So you have to ask, how does a multi-million-dollar aviation team make a mistake of that massive scale? Well, the root cause of this near tragedy is actually kind of mind-blowing. The ground crew simply mixed up two very different units of measurement. They calculated the required fuel using pounds per liter instead of kilograms per liter. So, by the time that plane was in the air, its fate was mathematically sealed. Miraculously, the pilots managed to glide to an emergency landing. There were no casualties, thank goodness, but the aircraft was heavily damaged. The crucial takeaway here is that using standard SI units everywhere completely avoids these types of deadly conversions. A simple, universal agreement on how we measure the world is quite literally all it takes to prevent these catastrophic, high-stakes errors from ever happening in the first place. In today's explainer, we're going to unpack the vocabulary of science to understand how we avoid these disasters. We'll be looking at the high-stakes fuel mix-up, why standard units matter, laws, theories, and principles, the power of prediction, and finally, testing our predictions. Section 1. The high-stakes fuel mix-up. So this breakdown shows the exact incident we were just talking about. It perfectly illustrates the extreme consequences of not speaking the exact same scientific language. I mean, pounds and kilograms are vastly different measurements. When those ground crews used pounds instead of kilograms, they practically doomed that flight. It's a really stark reminder that standardizing our units isn't just some boring academic exercise, it has intense, literal life or death impacts in the real world. Section 2. Why standard units matter. Let's zoom out from that dramatic aviation crisis for a second and look at our ordinary daily routines. Take a look at this peaceful vegetable seller using a simple pan balance. When we go buy rice or vegetables, we fully expect a kilogram to mean the exact same amount everywhere we go. Just imagine the sheer chaos and arguing if we use totally different weights in every single town. Thankfully, our measurements are anchored in agreed international standards, not just local objects or someone's personal opinion. Standard units do two incredibly vital things for us. They allow scientific results from anywhere on the planet to be accurately compared, and they ensure absolute fairness in daily life and trade for literally everyone. Section 3. Laws, theories, and principles. Okay, so now that we have a standard language for measurement, how do scientists actually organize their understanding of the world? As observations are tested over time, we use very specific vocabulary. First up is a law. A scientific law simply describes a regular pattern observed in nature, and it's often expressed mathematically. Think about Newton's laws of motion. They elegantly explain exactly why you feel that sudden physical jerk forward when the bus you're riding in slams on the brakes. Now, building on that foundation, a theory goes a vital step further. While a law describes the pattern, a theory provides an explanation of exactly why those patterns occur, and it's usually based on a massive mountain of evidence gathered over time. For instance, atomic theory doesn't just tell us molecules exist. It explains exactly how they form from individual atoms. And I really want to act as a bit of a mythbuster here, using this fantastic quote from the source. In science, a theory does not mean a guess or an untested idea. We hear people say, oh, well, it's just a theory all the time in casual conversation. But in science, a theory is a rigorous explanation based on careful testing and critical examination. And the best part, these ideas are always open to improvement as new evidence arrives. That self-correcting nature is exactly what makes science so incredibly reliable. Finally, we have a principle. Principles are essentially broad ideas that help us make sense of specific situations. A great example of this is the principle of conservation of energy. You apply this broad idea to understand exactly what's happening physically when you're expending all that energy climbing up a steep flight of stairs. Section 4. The power of prediction. This is honestly one of the most remarkable strengths of science. Once laws, theories, and models are well established, they basically become a sort of crystal ball. They allow us to look into the future and anticipate what will happen under totally new conditions, sometimes before an experiment is even performed. It's a phenomenally powerful tool that drives human exploration. And we aren't just talking about predicting complex quantum states in a lab here. Look at these everyday examples. Using ideas about motion, we can predict exactly how far a kicked football will travel. Using chemistry, we can estimate how soft a loaf of baked bread is going to be. Using biology, we can accurately predict how your breathing will change while you're out for a run. These aren't just guesses. They are reasoned expectations based entirely on evidence. But here's perhaps the most exciting part. What happens when we get it wrong? When predictions do not match our observations, scientists don't just throw their hands up and quit. They go back and carefully re-examine their assumptions, their models, or their measurements. Failing predictions are actually incredibly powerful learning tools that drive us toward a much deeper, more accurate understanding of our world. Section 5. Testing our predictions. So, how exactly do we check if a prediction is scientifically valid rather than just a random guess? Check out this great example. Varsha casually tells her friend Meghna it's going to rain this afternoon because the clouds look dark. Now, that's a prediction, sure, but how could Meghna actually scientifically test us? I really want you to think about this central question. If you wanted to test whether it will actually rain, what takes a question from a simple yes or no to something that's scientifically testable? Well, Meghna needs to ask questions that seek out measurable evidence based on past patterns. She could ask, what was the condition of the sky the last time it rained? What is today's humidity? Is it above 80% like it was during the last storm? What's the current wind speed and direction? Is the temperature dropping? By listing out these specific questions that rely on hard, measurable data, Meghna elevates a casual guess into a rigorous, scientifically testable prediction. Let's bring all these concepts home with a quick pause and ponder exercise. I highly encourage you to try applying everything we've just unpacked in this explainer to your own daily life. Think of a recent prediction you made. Maybe it was about who would win a cricket match or how long your drive to work would take today. Was it genuinely based on measurable evidence and solid reasoning, or was it basically just guesswork? How could you use the language of science to dramatically improve your own everyday predictions? Keep asking those measurable questions, keep looking for the evidence. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you on the next one.